All right, here's the last homework video for the unit. We want to sketch a portion of a function f whose derivatives have the following characteristics. So if f prime is greater than 0, that means f prime is positive, and f double prime is positive. We should translate these into statements. So that is telling me f is increasing, or f is going up, while f is concave up. So going up, concave up, that. If f prime is less than 0, that's f prime is negative, and f double prime is negative. So that's f decreasing in its values. So f is going down, while it is also concave down. Going down, concave down. Okay, f prime positive, f is going up, f double prime negative, f is concave down. Going up, concave down. F prime is negative, f is going down, f double prime is positive, f is concave up. Going down, concave up. All right. Now it's like the same questions here, only just worded differently. F prime is negative and increasing. Okay, so if f prime is negative, f is going down. If f prime is increasing, something is increasing if its derivative is positive. So if f prime is increasing, f prime's prime or f double prime is positive. So f prime negative, we talk about f decreasing if f prime is negative. If f prime is increasing, its derivative is positive. This is telling me f is concave up. So decreasing, concave up, we got that. F prime positive, that means f is increasing. F prime is decreasing. That means its derivative is negative. That means f is concave down. Going up, concave down. F prime positive. F is increasing. F prime increasing. Its derivative is positive, which means f is concave up. Going up, concave up. F prime is negative, f is decreasing, f prime is decreasing, its derivative is negative, f is concave down, decreasing, concave down. You could also think about, tangent slopes of f prime. F prime values. Negative, 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 but negative and getting more negative. Here, f tangent slopes are positive, but they are getting more positive, so they're increasing. Tangent slopes are positive, but they're getting less positive. Tangent slopes are negative, but they're getting less negative, means they're increasing in its values, getting closer to 0. If f prime is positive, f double prime is 0, that means f is going up, but no concavity. Straight line. And then f going down, but no concavity. All right, given the table of values, what would be an educated guess? What would an educated guess be for the sides of f prime and f double prime given the select values of f? Sometimes it's helpful to kind of sketch these to see. And if I have a point 1, 1, 2, 3, 3, 7, you can see I'm increasing, but at an increasing rate. So increasing at an increasing rate. That's increasing where the derivative is increasing. This would be increasing, concave up. sometimes it's tough to say like increasing at an increasing rate, but you can kind of see like increasing in concave up. If I go 7, 3, 1, we can see we're decreasing, but you gotta be careful. Like if we're not spaced out correctly, you might not see what we should be seeing. 7, 3, 1. We should be decreasing at an increasing rate. So that means like I'm decreasing, my first derivative is positive, but at an increasing rate means my slopes are getting less negative, trending towards 0, which means they're increasing, or we're concave up. 2, then 5, then 4. I think I made a mistake when I put these values in here. So like 1, 2, 2, 5, 3, 4. I think I meant to do 2, 4, 5. Let's change it to 2, then 4, then 5. Because like we'd have to change signs. F prime is going to have to go from like positives to negatives. 2, then 4, then 5 should be increasing but concave up. Increasing but concave down. 2, 4, 5. You can kind of see like I'm adding 2, then I'm adding 4. So I'm increasing but at an increasing rate. Subtract 4, subtract 2. I'm decreasing at an increasing rate. Add 2, add 1, increasing at a decreasing rate. So increasing at a decreasing rate, concave down. 2, then 4, then 6. I'm increasing at a constant rate. I would probably guess that 2, 4, 6. My first derivative would be positive, but my second derivative would be equal to 0. That's if like things are consistent. 1 to negative 1, I'm subtracting 2, then I'm subtracting 3. So like I go from 1, 1 to 2, negative 1 to 3, negative 4. I am decreasing at an increasing rate, at a decreasing rate. So I'm decreasing, but my tangent slopes are getting more and more negative. I'm concave down. It's tough with the decreasing, increasing. It confuses me because it's like, aren't I decreasing at an increasing rate because I'm getting like steeper and steeper to the negative? But you think about f prime values are going to be getting more negative, which means they are decreasing in their y values. Tricky. Here, I would say that I'm constant with no concavity. All right, do a full curve sketching analysis to find the intervals on the following functions have specific characteristics. We want f is increasing and concave down, and we want f prime negative and decreasing. All right, so we're going to have to do an analysis of f prime and its signs and f double prime and its signs. So here's f prime. We will find its important points where we could change signs. And we'll go ahead and do f double prime as well. See important points where it possibly changes signs. We don't have to worry about the undefined. So I get 0 and 4 here. I'll get 2 here. So popping over here, let's throw down sign analysis of f prime, 0 and 4. And then make sure f double prime's value 2 is in between. That way we keep track of things. Using test points into f prime and into f double prime, plugging 5, positive times positive, plugging 1, positive times a negative, plugging in negative 1, negative times a negative. Plugging in 3, into f double prime, that's positive. Plugging in 1 into f double prime, that would be negative. Okay, so what is this telling me? This is when f is increasing, decreasing, increasing. This is when f is concave down, concave up. We could also say this is when f prime is decreasing and increasing, right? So the derivative of f prime, f double prime, something is increasing or decreasing if its tangent slopes are negative or positive. So with that analysis, we could see f is increasing and concave down. So for number 1, increasing, concave down, the only time when the signs of those agree are from negative infinity to 0, or x is less than 0. F prime is negative and decreasing. So if f prime is negative, okay, cool. If f prime is decreasing, its tangent slopes are negative. So I want negatives for both of them. So I'm looking at, here's 1, here's going to be 2. F prime is negative here and decreasing, which means its tangent slopes are negative here. So I'm going to be saying from 0 to 2. Okay. Let's do 9x squared minus 3x cubed. All right. 18x minus 9x squared. Find when this possibly changes sign. X is 0 and 2. Do the same for the second derivative. Sign analysis. For f prime and f double prime, 0 and 2, 1. Plugging in 3, positive, negative. Plugging in 1, positive, positive. Plugging in negative 1, negative, positive. Plugging in 2, 18 minus 36. Plugging in 0, 18 minus 0. Okay? So with that, we know when f is going down. We know when f is concave up or concave down. We also know when f prime is going up or going down. You may use this if you want to, but I don't know. I don't think it's necessary. It's just good to say, like, okay, if f double prime is positive, f prime must be increasing. All right, so if f is decreasing and concave up, decreasing, concave up, again, we're talking about this interval. It just so happens that interval. So from negative infinity to 0, or x is less than 0. And then f prime positive and decreasing. So f prime is positive here. F prime is decreasing when the second derivative is negative, when its derivative is negative. So positive and the second derivative negative here. So that's from 1 to 2. All right, next one. Increasing, concave up, f prime negative and increasing. Let's just go ahead and do the sign analysis. And second derivative, 60x squared minus 20x cubed plus 20x squared, 3 minus x. Don't have to worry about the undefines. Here we go. F prime, F double prime. Zero and 4, 0 and 3. Make sure things are lined up, just so you can answer these questions carefully. All right, so 5, that'd be a positive. 4 minus 5 is a negative, so it's negative. 1 would be a positive. 4 minus 1 is a positive. Negative 1, it would retain its sign because it's being cubed, so that's a negative. 4 minus negative 1 is a positive, so this is a negative. Into the second derivative. 4, positive. 3 minus 4 is a negative. Positive times a negative. 2, positive, positive. Negative 1. A positive because it's a negative being squared, and 3 minus negative 1 is a positive as well. Okay, so this is telling me f is going down, then going up, then going down. This is telling me f is concave up, then flattening out completely, then concave up, and then concave down. It's also telling me that f prime is going up, then flattening out, then going up, then going down. When is f increasing and concave up? F is increasing here, f is concave up here, as well as here. But when are they the same? Is from 0 to 3. When is f prime negative and increasing? F prime is increasing when its derivative is positive. So I'm looking for f prime being negative and f double prime being positive. So it's negative here, it's positive here and here. So it's negative and f double prime positive here. From negative infinity to 0. X is less than 0. This is x is between 0 and 3. Okay, next one. X to the 4th minus x squared. All right. X squared minus 1. That gives me x plus 1, x minus 1. 3 points versus the other ones that are just 2. Second derivative, 4x cubed minus 2x. Factor out at 2x. And I get 2x minus 1. I get 0 and 1/2. Oh, that's not right. Square. 2x times 2x squared is 4x cubed. So 2x squared, you will need to solve. You could factor this if you wanted to, but it's easier to solve. 2x squared equals 1. X squared equals 1/2. X equals plus or minus root 1/2. So x equals 0, negative root 1/2, positive root 1/2. Don't be afraid of crazy numbers. Try to give you easy numbers, but sometimes you'll have answers that are I guess, more complicated in your eyes. What's important is to keep track of locations. -1, 0, 1, I'm going to space out more than 0. Negative √1/2, I know it's between -1 and 0. Positive √1/2. Doing my sign analysis, and I'll go ahead and graph this when we're done, that way we can see all of our work in its glory. If I plug in 2, positive, positive, positive. If I plug in a half, positive, positive, negative. If I plug in -1/2, positive, positive, negative. If I plug in -2, positive, negative, negative. Okay, I've done that for a while, so that's why I'm quickly able to do it. If you need to write down, positive times negative, do that. For a half, it's a positive, and a negative. For a half, again, it's positive, positive, negative. And for 2, positive, positive, positive. For f double prime, I'm using this. And for f prime, I was using this. If I plug in just a large value, positive 2 times like 5 squared minus 1, definitely going to be positive. Okay. Now, a number between 0 and √1/2. What am I going to do? Just think about just a very, very small positive number. Okay, like 0 from the right. Don't let that confuse you, but 2 times a very small positive is a positive. Okay, great. Now, if I take a very, very, very small number, square it and multiply it by 2. I'm talking about a super small number. Square it times 2, it's going to be a super small number. If I subtract 1, that's going to make it a negative. That's why I know this is a negative. Now, if I go to the other side of things, a very small negative number. Well, 2 times a small negative number is a very small negative number, but it's still negative. And then a very small negative number squared is going to be a very, very small positive number times 2. Stays as a very, very small positive number minus 1. That'll be a negative. So this actually switches to be a positive. -5. 2 times -5, 2 times -5 squared. -5 squared makes it a very large positive, times 2 minus 1. That's going to be a positive. Okay? So, what we will see when we graph this is f is going up until -1, going down to 0, flattening out, but then going down after that, and then going back up. Whereas f double prime tells me f is concave down, then concave up, then concave down, and concave up. We could combine all of these if we wanted to, and we could have done it for all of them, but it's not necessary. But there are some situations where you'll be asked to sketch the curve. So let's just do it for here. Example for curve sketching. And we did this in our notes. We put all of the values down. Increasing concave down, decreasing concave down, decreasing concave up, decreasing concave down, decreasing concave up, increasing concave up. So being able to do this sign analysis shows me that my graph is going to look like this. Boom, 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 boom. Let's just go ahead and sketch that. We'll see that when I graph this. 1/5 x to the 5th minus 1/3 x cubed. Can't really see it, but zoom in. Enhance. Okay. Increasing concave down until -1. Great. Then decreasing concave up until negative root a half. Here we have a point of inflection. You can see we're concave down, and then we switch to being concave up. At 0, we switch from being concave up to concave down. At positive root 1/2, we will switch from being concave down to concave up. At 1, we'll hit a minimum, and then we'll go from there. Okay? So we're able to kind of get that general sense of what this function looks like by examining the signs of the first and the second derivative. If I were to answer the problems assigned to me, though, when is f decreasing and concave down? Decreasing and concave down, I have two intervals. Negative and negative here, and negative and negative here. This is why it's very, very important to keep track of like the order of your values. So I'm going to say, I'll use interval notation, from -1 to negative root 1/2, and from 0 to 1 root 1/2. F prime positive, let me edit this. F prime positive and increasing. If f prime is increasing, f double prime is positive. So I want f prime positive and f double prime positive. Okay, I'm positive for f double prime here. I'm positive for f double prime here. The only time that I'm positive and positive is here, from 1 to infinity. Okay. Sweet. Given f prime, what is f increasing and concave down? Great. Well, I can do my analysis of f prime. And I have zeros at -1 and at 3/2. Plug in 4, positive, positive. Plug in 0, positive, a negative cubed, negative. Plug in -2, positive, negative. Okay, great. Now, my friends, I'm shocked I gave you this answer, this question, but maybe I'm overthinking it. Maybe it's a good question. I need the second derivative. I got to use the product rule and the chain rule. Ready? So this is the first, this is the second. Here comes the product rule. Derivative of the first. The first has an outside and an inside. That's stuff squared and then x plus 1. Derivative of the outside is the 2 stuff. The derivative inside is just 1, so that's why I have the 2 stuff. Times the second. Plus. Derivative of the second. The second's got outsides and insides that will affect the derivative. The inside's derivative is 2. The outside's derivative, 3 stuff squared. So the derivative of the second piece is 3 2x minus 3 squared times 2 times the first piece, x plus 1 squared. I want to set this equal to 0 and solve. Guess what, my friends? We need to factor. Let's see if it factors nicely. What can I pull out of this and this that is shared? They both have a 2 I can pull out. Okay. They both have an x plus 1 that I can pull out. And they both have 2x minus 3 squares. So I'm going to factor that out. And I get a second derivative of the factored out 2 times x plus 1 times 2x minus 3 squared times This is gone. I'm just left with 1, 2x minus 3. Plus, the 3 stays. These 2 are gone. This 2 is gone. One of these x plus 1s is gone. Okay. Simplifying that, I get 2 x plus 1, not x plus plus. X plus 1, 2x minus 3 squared. This is 3x plus 3. So that's 5x. Oh, minus 3 plus 3. That's gone. Okay, great. It's actually not that bad. We get x equals -1 is important. 3/2 is still important, but now 0 is important. Okay, so f double prime. -1, 0, 3/2. Sign analysis. All right. Positive, positive. This is always positive. That's good to know. So positive, definitely positive, positive, positive. 1. Positive, 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 positive. -1/2. Negative, positive, positive, positive. So negative, positive, positive, positive is going to have a negative. -2. Negative, this is a positive. This is now a negative. This is a positive. So positive, negative, positive, negative. It's 2 negatives, 2 positives, positive. I don't know what f is. You know, I don't know what the original function is. I do know what I hope. If this freezes on me and like disappears, I'm gonna flip. I've put in a lot of work here, but you see that spinning. Okay, we're good. All right, here we go. F is going down, flattening out, going down, going up. F, concave up, concave down, concave up, concave up. Where is F increasing and concave down? Increasing, concave down. Never. There's no interval. Where it's both increasing and concave down. When is f prime negative and decreasing? F prime is decreasing when its derivative is negative. So f prime is negative and f double prime is negative. F prime is negative, f double prime is negative. Here. There. So just from -1 to 0. All right. All right. Given a table of values of a twice differentiable function, what must be true for all cases of f? Here's what I want you to get away from this problem in preparation for problems like this that you'll see on the test on the AP exam. It says true for all cases. We got these points. And for the previous table problems, I told you to sketch. If you sketch these points, 1, 10, 2, 15, 3, 17, 4, 12, 5, 10. What every student assumes is that you connect those points in a smooth way. However, that's only a possibility. This is why it says true for all cases. This could be the graph of f. I'm going to show you right here. This is a possibility for f. It's not this. This is also a possibility. This is just one case. But we need to keep this in mind. So I'm going to write that possible f of x. So is f of x positive on the interval from 1 to 3? Well, if you think, oh yeah, 10 to 15 to 17, it is. No, not if I draw f like this. So no, that doesn't have to be true. Is the second derivative negative? Oh, well, it's like add 5, add 2, so maybe I'm actually concave down everywhere. No, it doesn't have to be. I'm concave up, concave down a lot. So don't assume things are going to be a nice, smooth connection. In the previous table problems, I said, like, take an educated guess. Oh, the derivative at 3 has to be 0. I'm going to have a max at 3. No, I don't necessarily have a max at 3. I can go through 3 to keep going back up. So no, this is not necessarily true. Second derivative has to be positive from 3 to 5. I go from 17 to 12 to 10, so that means I subtract 5, subtract 2. So it means I got to be, no, not necessarily. So this red is not, it does not have to be F. But what has to be true is this. Why? F prime of x equals 0 for some x between 1 and 5? Oh my goodness. We are twice differentiable. That means this function is differentiable. No matter how I sketch f, whether it's the red graph, the black graph, or anything else, f has an average rate of change, a secant slope, since we have the point 110 and 510, the average rate of change, the secant slope, is 0. The mean value theorem, if you remember, says we're going to have a tangent slope equal to the average rate of change, no matter what, since the function is differentiable. This is true. There's going to have to be an f prime equal to 0, no matter how I sketch the graph of f. So, true. This is the only one that has to be true. Okay, so let's keep that in mind. These table problems don't assume things are connected easily. All right, back to our friends, the graphs of f prime. We're going to do a sign analysis of f prime and f double prime at the same time. Remember, f prime sign, since I'm given f prime, I have negative values below the x-axis, positive values above. So I'm going to be negative until negative 3, positive until 2, negative after 2. F double prime, slopes of tangents of f prime, positive, positive, positive slopes, positive slopes, positive slopes, until 0. Negative slopes, negative slopes, negative slopes, negative slopes until 2. I mean, until forever. When is f increasing and concave down? Well, remember, f is going to have to go down, then up, then down. That also, this tells us f is concave up and concave down. F is increasing and concave down here. That's when they overlap. 0 to 2. One is f prime negative and increasing. F prime is increasing when its derivative is positive. So when is f prime negative and f double prime positive? F prime negative, f double prime positive here. And that's it. Negative infinity to negative 3. Okay, same deal. I got positive f prime values until negative 2. Then I got positive f prime values until 1, negative in values until 3, positive values after that. F double prime, slopes of f prime, negative slopes until negative 2, positive slopes until 0, negative slopes until 2, and positive slopes after 2. One is f decreasing and concave up. F prime is negative, f double prime is positive. I might as well just write it down. F is going up, going up, going down, going up. F is concave down, concave up. Concave down, concave up. F is decreasing and concave up here. So that's from 2 to 3. One is f prime positive and decreasing. F prime is decreasing when its derivative is negative. So f prime is positive. And f double prime is negative here. And here. So negative infinity to negative 2 and 0 to 1. How many critical points relative to extrema and points of inflection does f of x have? So critical points, remember, just when f prime is 0 or undefined. It's not when f prime and f double prime are 0 and undefined. So my critical points are at negative 2, 1, and 3. However, my relative extrema are just x equals 1 and x equals 3. X equals 1 is a max. X equals 3 is a min. Now f is going up or going down. Points of inflection are at negative 2, 0, and 2. We do change sign. At all those locations. All right, f prime, f double prime. A lot of sharp points. I'm intimidated. Don't be intimidated. Just do what you've done before. 1, 2, 3. Looks like at negative 3, f prime changes signs from positive to negatives until negative 1, where it's positive, until 1, where it's 0, but then it goes positive again. I have 3 critical points, x equals negative 3, negative 1, and 1. I have 2 relative extrema. X equals negative 3 is going to be a max, and x equals negative 1 is a min. F is going up, going down, going up, flattening out, going up. Points of inflection, okay. Look at tangent slopes. Negative tangent slopes. Negative, 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 until negative 2. Negative tangent slopes. At negative 2, it's undefined. It's okay. The tangent slope of f prime here at this sharp point is undefined, but that's okay. I don't know how it's going to look like on f, but like it could be just like a sharp point or a vertical tangent or something like that. Then at negative 2 to 0, the tangent slopes are positive. And then from 0 to 1, they are negative. And then after 1, they are positive. Just look at the tangent slopes. So f, concave down, then concave up, then concave down, then concave up. So we have points of inflection at negative 2, 0, and 1. Where is f? Increasing and concave down. Increasing, concave down. Increasing, concave down. That would be it. So from negative infinity to negative 3, and from 0 to 1. All right, this is the graph of f. So you probably would be told that x equals 1 is a point of inflection for f. 0 is a min, 2 is a max. But you can kind of see that. When is f prime positive and f double prime positive? I'm translating this to when is f going up and f concave up. When is f going up and concave up is just from 0 to 1. Here I'm increasing and I'm concave up. Where is f prime positive and decreasing? So when is f going up? If f prime is decreasing, its derivative is negative. So this is translating to and concave down. Going up, concave down here. So from 1 to 2. Order from least to greatest. F of 2, 1, 2. F of 2 is a positive value. So f of 2 is positive. Okay, great. F prime of 2. Oh, the slope of the tangent to f at 2 is 0. I look at the slope of the tangent to f. F double prime of 2. Okay, well, the concavity of f is concave down, so that means the second derivative is negative. So if I'm ordering them, I got my negative value, which is going to be less than my 0 value, which is going to be less than my positive value. It's interesting. Last question. Almost there. When is f prime negative? That means f is going down. Decreasing. F double prime is negative. That means f is concave down. We probably can see f is going down and concave down, probably here. And that's it. It's going down, concave up. Going up, concave down. Or probably going up, concave up until here. Then going up, concave down. Going down, concave down. So I would say this is just from negative 1 to 0. You would be told in a question on like a test and a quiz that you have like a min, a point of inflection, a max, a point of inflection, a min, and that's just a 0. When is f prime positive and decreasing? That means f is going to be going up. F prime decreasing means its derivative is negative. So f is concave down. When are we going up and concave down? It looks like we are going up and concave down here. It's not obvious. Going down, concave up. Going up, concave down. Probably I would tell you that this is a point of inflection and this is a point of inflection. So from negative 2 to negative 1. Order the following from least to greatest. We're looking at negative 4. Okay. 1, 2, 3, 4. Okay, well the point, the function value is 0. F of negative 4 is 0. The tangent slope is negative. All right, so f prime of negative 4. that's negative. F double prime, well, if I look at the concavity of f is concave up at -4, so the second derivative is positive. So if I were to order these from least to greatest, I would have f prime, which would be less than f, which would be less than f double prime. Get it?